In today's note, we are going to continue on looking at our exponent rules, and we're going to look at our zero and negative exponents. So to help us out, or to at least start to investigate that, we're going to use some patterning to evaluate the following. So 2 to the power of 4 we can do on our calculator, and we get 16. 2 to the power of 3, we get 8. 2 to the power of 2, we get 4. And 2 to the power of 1, we get 2. We could evaluate 2 to the power of 0 on our calculator, but let's use some patterning to figure this out. If I go from 16 to 8, I've decreased my exponent by 1, and the relationship is that I've divided by 2. If I go from 8 to 4, I've decreased my exponent by 1 again, I've divided by 2 again. And we can see that every time we decrease an exponent, we're dividing by 2. And again, this is just the case because our base is 2, so we're decreasing, or we're dividing by 2 every time. If I continue this pattern, what should 2 to the power of 1 be? To figure that out, 2 divided by 2, we get 1. And you can double check that on your calculator. If I continue that patterning, 2 to the power of negative 1, I get a half, or 1 divided by 2. 2 to the power of negative 2, again continue the patterning, 1 half divided by 2 is 1 quarter. 2 to the power of negative 3, continue that pattern, 1 quarter divided by 2 is 1/8. And lastly, 2 to the power of negative 4, I've decreased my exponent by 1 again. Take the last answer, 1/8 divided by 2, I get 1 over 16. Looking at this, looking specifically at my negative exponents, the 2 to the power of negative 1 and so on, is there a connection between our other exponents that we've already found? And hopefully we see that all the bottom numbers, or the denominators of my fractions, pair up with the positive versions of my exponents. So if I look at 2 to the power of negative 1, that's the same thing as saying 1 over 2 to the power of 1. 2 to the power of negative 2, or 1 quarter, is the same as saying 1 over 2 to the power of 2. 2 to the power of negative 3, 1/8, is the same as saying 1 over 2 to the power of 3. And lastly, 2 to the power of negative 4, or 1/16, is the same as saying 1 over 2 to the power of 4. So hopefully we're beginning to see what the rule is, or what the pattern is when we have negative exponents. In the next part, I want to use the exponent laws that I already know to help simplify the following, which will again help me see what these zero and negative exponent rules are in a different way. 2 to the power of 5 divided by 2 to the power of 5. When we divide powers, we subtract our exponents. So in this case, 5 minus 5, or I get 2 to the power of 0. If I wanted to expand this, or show this in expanded form, 2 to the power of 5 is just 2 times itself 5 times. And then that's all divided by 2 to the power of 5, or 2 times itself 5 times. So from here, we can figure out what this equals. Because I have an even number of 2's on the top and the bottom, they all cancel each other out. And when they all cancel each other out, or basically when I have a whole, that's equal to 1. So we know that looking at this expanded form that it equals 1, so that means, therefore, 2 to the power of 0 equals 1. And from our patterning above, we also found that out as well. If I do the next example, 2 to the power of 2 divided by 2 to the power of 5, again, use my division or rule for dividing exponents. I subtract them, so 2 minus 5, I get 2 to the power of negative 3. If I wanted to look at this in expanded form, 2 to the power of 2, there's two 2's, and because it's divided by 2 to the power of 5, there's going to be 5 2's on the bottom. If I go through and cancel things out similar to the last example, cancel one on the top, one on the bottom, another one on the top, and another one on the bottom, I'm left with 1 on top, and on the bottom I have 3 2's all multiplied by each other, or 2 to the power of 3. So that means that 2 to the power of negative 3, which I found out by using my product or my division rule, is equal to 1 over 2 to the power of positive 3. And we have seen that before in the patterning above. So hopefully from these two relationships or these two investigations, we can see what our rule is for when we have a 0 exponent and when we have a negative exponent. When we have a 0 exponent, any base raised to an exponent of 0 equals 1. So it doesn't matter what the base is. It could be the largest number you think of. If you put it to the exponent of 0, it will equal 1. Any number, any variable to the exponent of 1 or the exponent of 0 equals 1. When we have negative exponents, such as x to the power of negative a, if I want to express that as a positive exponent, I have to flip it. So it becomes 1 over x to the power of a, and that exponent now becomes positive. If I have a fraction as my base to begin with, and it's to the power or to a negative exponent, I flip that fraction and the exponent becomes positive. So those are the two rules, one for 0 exponent and one for negative exponents. So now we're just going to look through a few examples involving those two rules. In the first one, 5 to the power, or we want to evaluate these pairs of expressions, and we do not want to use decimals. You can evaluate an exponent or a negative exponent on your calculator. It will give you a decimal, however. And we don't want to use decimals though when we evaluate them, just because we want to be precise. So let's start off 5 to the power of 3. This we can do on our calculator. Positive exponents are fine. 5 to the power of 3 is 125. If I want to do 5 to the power of negative 3 though, I first need to turn this into a positive exponent. This becomes 1 over 5 to the power of positive 3. Why did I put it over 1 or under 1? Well, 5 as a fraction is 5 over 1. So I flip that and it becomes 1 over 5. The exponent changes to be positive, so it's positive 3 now instead of negative 3. I can expand this or evaluate this because I know 5 to the power of 3 is 125. So that means that 5 to the power of negative 3 equals 1 over 125. Let's try that again with the second one. Negative 3 to the power of 6, it's a positive exponent, so I can evaluate this just as is on my calculator, and I get 729. If I want to do negative 3 to the power of negative 6, because it's a negative exponent, I need to make it positive. So I need to flip this, and it's over an invisible 1, so when I flip it, it becomes 1 over negative 3. The exponent now becomes positive, so to the power of 6. If I want to evaluate this further, I already know what negative 3 to the power of 6 is because I solved that or evaluated that in the last part. And negative 3 to the power of 6 is 729. So that's my exact value. If you were to do that on your calculator, you would get a long decimal that's not very precise. So this is the exact value. And again, when we're evaluating expressions or evaluating negative exponents, we tend to want to have the answer as a fraction, not as a decimal. So let's go through the next example where we want to write each expression with a positive exponent, and then we want to simplify that expression. So if I look at 3 to the power of negative 4, if I want to express it with a positive exponent, I need to flip it. So it becomes 1 over 3, and now my exponent becomes positive, or 1 over 3 to the power of 4. To evaluate this, I can figure out what 3 to the power of 4 is, which is 81. So this becomes 1 over 81. 7 to the power of negative 3, flip it, 1 over 7 to the power of 3. I can evaluate 7 to the power of 3, and it becomes 1 over 343. For C, again, same steps. Flip it, put it under 1, becomes negative 2 to the power of positive 5, so my exponent now becomes positive. I can evaluate the bottom part, so this becomes 1 over negative 32. For D, same idea. Flip it, because it's a whole number, it's over 1, so it becomes 1 over negative 5. 6 becomes positive. I can evaluate just the bottom on my calculator and put it under 1. So negative 5 to the power of 6, 15,625. And I put that on my denominator, or the bottom part of my fraction. So I've expressed them as a positive exponent, and then I've evaluated or simplified them. Moving on to number 3, again, I want to do the exact same thing. I want to express or write each power as an expression with a positive exponent, and then simplify that expression. The only difference here is that now I have fractions. We're still going to treat it the same. When we have a negative exponent, if we want to get it positive, we have to flip our fraction or flip our base. In this case, 1 over 3 becomes 3 over 1, and the exponent changes to positive 4. This is just another way of saying 3 to the power of 4, which I can evaluate, which is 81. For B, same thing. Flip my fraction, becomes 5 over 1 to the power of now positive 3, so it changes. Once I flip it, that exponent becomes positive. 5 to the power of 3 is 125. For C, again, same thing. Flip my fraction, becomes 6 over 1, or 6. The exponent changes to be positive. 6 to the power of 2 is 36. So again, I've expressed it as a positive exponent by flipping my base, and then I simplified it by just evaluating it. Number 4. Number 4 is, again, the same thing, except we're going to combine some of our rules. So we want to write each expression as a single power with a positive exponent and then evaluate. And we do not want to use decimals. So if we get a negative exponent or a fraction, we do not want to use decimals. So I can't just enter this into a calculator. I need to actually use my power rules to express it as a single power, and then use my understanding of that to evaluate it. One thing we want to keep in mind, we do not want to change negative exponents to positive until we are ready to evaluate. So we need to get it to a single power first, and then we worry about changing it to a positive exponent. So for example, with the first one, 8 to the power of 4 times 8 to the power of negative 2. With our power rules, we keep the base the same, and we add the exponents. So 4 plus negative 2, this becomes 8 to the power of 2. This I can evaluate. 8 times 8 is 64. For B, 8 to the power of 4 divided by 8 to the power of 4. When we divide our powers, we subtract. So 4 minus 4, we subtract our exponents. Becomes 8 to the power of 0, and anything to the power of 0 is 1. For C, 4 to the power of 2 divided by 4 to the power of 5. because we're dividing, we're going to subtract our exponents. So we have 4 to the power of negative 3. Now that I've simplified it, now I can express it or change it to a positive exponent. Remember, we have to flip our base, so in this case it becomes 1 over 4, and that exponent of 3 becomes positive. So 4 to the power of negative 3 becomes 1 over 4 to the power of 3. This I can evaluate. 4 to the power of 3 is 64. For D, again, same thing. Simplify it down to a single power first, and then worry about changing it to a positive exponent. So because I'm dividing powers with the same base, I keep the same base and I subtract my exponents. So in this case, 2 divided by negative 3 becomes 2 minus negative 3 for my exponents. So it becomes 4 to the power of 5. This is already as a positive exponent, so I don't have to worry about changing it. And I can just evaluate this. I get 1024. E, even though I have a fraction, it's the same thing. I still want to leave my exponents the way they are until I get down to a single power, and then I'll worry about changing it to a positive. So I'm going to keep the base the same, 1 over 3. I'm multiplying powers, so I have to add my exponents. So negative 5 plus 7. This becomes 1 over 3 to the power of 2. And to evaluate this power of 2, or exponent 2, applies to both parts. So 1 to the power of 2, 3 to the power of 2, and this becomes 1 over 9. And again, you can reason that out, because 1/3 or 1 over 3 squared just means 1 over 3 times 1 over 3. When I multiply fractions, I multiply just the top and just the bottom, so essentially I'm getting 1 times 1 over 3 times 3, which is 1 squared divided by 3 squared. So that's why that exponent of 2 applies to both parts. F, again, same idea. I have my exponents, or I have my same base, so I'm going to keep the same base. I'm adding my exponents, so 5 plus negative 7. Again, the reason I'm adding is because I'm multiplying powers with the same base. So again, going back to the last lesson. When I add my exponents, I get 1 over 3 to the power of negative 2. Now I have a negative exponent. I am down to a single power though, so I can evaluate this, or I can change this to a positive exponent. In order to do that, I need to flip my base. In this case, I'm flipping my fraction. It becomes 3 over 1, or 3. And now my exponent changes to a positive 2 instead of a negative. I can evaluate 3 squared, and I get 9. For G, 2 to the power of negative 5 to the power of negative 2. The exponent rule when I have a power to a power was that I multiply my two exponents. So negative 5 times negative 2. I get 2 to the power of 10, or positive 10 specifically, and this works out to 1024. Lastly, 2 to the power of negative 5 divided by 2 to the power of negative 10. I have two negative exponents, but I want to keep them, or I don't want to do anything with them until I simplify to a single power. When I divide exponents, again, the rule is to subtract my powers, or sorry, my exponents. So negative 5 minus negative 10. I get 2 to the power of 5. It's already in a positive exponent, so I don't need to worry about changing anything now. And 2 to the power of 5 is 32. So the main thing that you should get from this note is that when you have an exponent of 0, it becomes 1. Any base to the power or to the exponent 0 is always going to equal 1. And when you have a negative exponent, how you make it or change it to a positive exponent is that you flip your base and then your exponent becomes positive. So again, those are the two other rules that we're adding on top of our multiplying powers rule, dividing powers rule, and power to a power rule. All three of which we've covered in this last question. And if you need to review that, please look back at the last note.